Okay, so in this video, we're going to start scientific math. And so this is where we're just going to incorporate math into science, because really that's what we have math for. I mean, we learn lots of concepts in math about how to find variables and find unknowns. And then when we get into science class, that's where we apply those concepts that we've learned. So I'm going to try to hit present on this PowerPoint, and then we're going to get started. Let's see. Okay. All right. Great. That works. So we're going to talk about scientific notation, dimensional analysis, significant figures, graphing, density and percent errors, and then accuracy and precision. Okay. There we go. All right, so first off, we need to know that there's two kinds of scientific data. There is quantitative data, and that's data that involves measurements and numbers. And then we have, involves measurement and numbers. Oh, I need to change my pen color. There we go. And then we have qualitative data, which is more of a description. So it's not really numbers. So qualitative data would be things like red light, and quantitative data would be things like the specific wavelength of light that we're talking about. Okay. There we go. So accuracy and precision. So accuracy is coming to the correct value or the standard value. It's how close you are to that target. If you're thinking about in terms of a target or a bullseye on a target. Accuracy is how close you are to the bullseye, how close you are to the correct value. Whereas precision is just looking at being able to be repeatable, being able to get a value repeating over and over again, where it's not necessarily in the right place, but you are getting the same number every time. So values being repeatable has to do with your precision. So most of the time we'll try and use those interchangeably, and that's really not the way we should do that. Accuracy means how close you are to the true value, whereas precision means how close are you getting the same value every time. It might not be true, it might not be the right one, but it's the same one every time. Okay? So here is a slide that demonstrates that. All right, so in this one, we are not accurate or precise. So you see you're off of the bullseye, and you have lots of different values going on in different directions. Here we are accurate and not precise. Here we are accurate and precise. So we're getting the same thing every time, but and it is in the same place every time. It's in the bullseye. The bullseye would be the correct value. And then if you are, let's see if I can hide that. There we go. And then if you are not accurate, but you are precise. So we're off from the bullseye over here, but we're all clustered together in almost the same spot. So those are our four different options. Of course, you want to be accurate and precise, but we just need to be able to know the difference between those two things. So not accurate and not precise would be not on the bullseye, but also not clustered together. Not accurate but precise would be that they're all clustered together. Accurate but not precise would mean you're in the general area, but you're also spread apart. So these are in the area of the bullseye. They're not off to one side or the other, but they are also not close to each other at all. And then accurate and precise would be in the bullseye every time you shoot. Okay? All right, so the next thing we need to learn how to do is learn how to take a percent error, because we need to know how far we are off in our calculations when we're in lab. So percent error is always measured by, there we go. Percent error is always the measured amount minus the accepted amount divided by the accepted amount. And we take the absolute value of that. Okay, absolute value. So if it turns out to be a negative number, you just switch it to a positive number because that's taking the absolute value. So what you get in lab, that's your measured amount. The accepted value is what you would look up. You subtract those two, divide by the accepted, and that gives us our percent error. It's how close we are to the accepted or true value. Whoops, wrong thing. So, percent error calculations. Let's look at an example, and we'll move on from there. Okay, it's hard to see this word, but it does say accepted right here. So a student determines the density of a substance to be 1.400 grams per liter. Find the percent error if the accepted value is 1.303. I'm sorry, I said that so backwards. 1.360 grams per milliliter. So what you're going to do then is just subtract those two numbers. So 1.400 minus 1.360. And then you're going to divide by the accepted value, which is 1.360, and multiply by 100. That comes out to be 2.9%. So that's a really easy calculation. You're pretty much just going to plug your numbers in where they belong and do the math that goes with it. All right, so this is one that you're going to try on your own. So a student calculates the density of iron as 6.8 times 10 to the, not 10 times 10, 6.8 grams per cubic centimeter by using lab data for mass and volume. The handbook reveals the correct value is 7.86 grams per cubic centimeter. What is the percent error? Okay, so on this, you're just going to take your measured minus your accepted divided by your accepted times 100. So 6.8 grams per cubic centimeter minus 7.86 grams per cubic centimeter. And we're going to divide that by 7.86 and multiply by 100. Okay, so take a minute, get your calculator out, and finish working that out and tell me what percent error that would be. Okay, so you should have had some time there to finish that calculation. So what we're going to do is take our measured value is the 6.80. Our accepted value is the 7.86. We subtract those two, divide by 7.86, and then times 100. So that would be, if you don't do the absolute value, it would be negative 13.5. But we always in these problems, we take the absolute value of that. So we basically just drop the negative sign off. Okay, significant figures. I want to start this just a little bit. And then on Wednesday, we will have another video on how to do significant figures along with a worksheet. So the cylinder should be read as 44.9 milliliters. 44 milliliters can be read with certainty. So you know, if you're looking at this, you know that the water level is, this is 40. Right there is 40. That's 42. No, 41, 42, 43, 44. And then here's 45. So we know we're right at 49. Or 44, sorry, we know we're right at 44 milliliters. And then that last decimal point right here, we kind of got to estimate. It looks like it's 0.9. So we estimate it as 0.9. So when I write that down, everybody knows that I was accurate to, I was right about the first place, I was right about the ones place, and I am estimating the first digit, but I'm pretty sure I'm right about that first decimal place. So that's what a significant figure is. It's all the numbers that you're sure of plus one that you had to estimate. Okay, so let's look at this one. Report out the volume measurement reading for the graduated cylinder to the proper significant figures. Okay, so we're looking at this and we know we're at 60. We know that's right. We know we're at 1, 2, 3. We're at 63. And then we are halfway in between 63 and 64. So that gives us 63.5, which is 3 significant figures because I don't have any zeros. So zeros are the only numbers that have rules that go with them for significant figures, because otherwise all non-zero digits are significant, so it doesn't matter if there's no zero in there. Okay, so here's our rules. All non-zero digits are significant. So that's why 63.5, there was 3 significant figures, because those are all non-zero digits. So here's another example. 65608.2 has 6 significant figures. We'll explain why, but the 0 in between the 6 and the 8 is also significant. So that's why we wind up with 6. This also has 6 significant figures because these 2 zeros in between 2 non-zero digits are significant, both of them. All right, zeros between non-zero digits. Zeros between non-zero digits are significant. So in this example, we can see that this 0 is significant because it's between 2 non-zero digits. This digit is significant because it's between 2 non-zero digits. Well, I keep going back to that same slide. I don't want it. All right, here's another one. Rules to the right of non-zero digits are not significant. So you can see these 3 right here are not significant, just the 1, the 4, and the 7, because they are to the right of a non-zero digit. 50 has 1 significant figure, again, because that 0 is to the right of a non-zero digit. And 1230 has 4 because that 0 is not to the right, it's to the right of a non-zero digit, but that decimal right there, that intentional placement of the decimal, means that you are estimating as best you can out to that decimal place. Okay. So zeros to the right of of the decimal and to the left of a non-zero digit are not significant. So you can see these 2 right here, pointing right there. Those are not significant. They are to the left of non-zero digits, and they are to the right of the decimal. So they are not significant. In this number at the bottom, these 5 are my significant figures. The 0 in front, again, it's behind a decimal, but in front of the 1, that means it too is not significant. Zeros at the end of a number and to the right of a non-zero digit are significant. So if they come at the end of the number, but they are to the right of a non-zero digit, then they are significant. So here's an example. This has 6 significant digits because these last 2 zeros, oops, come on. There we go. So these last 2 zeros right here, we have to think about those because they're at the end of the number. They are to the right of a non-zero digit. So are they significant or not? And yes, they are significant. All right, so these are a few practice problems. We'll just go over a few of these. Report the number of significant figures in these numbers. Okay, so the first one would have 6. The second one would have 4. The third one would have 2. When you have things in scientific notation, the 5 and the 2 there are your significant numbers. This one would have 1, 2, 3, 4, 5, 6, 7. This one would have 2. This one would have 5. Because that decimal at the end lets you know that everything before that and everything before it is significant. All right, so here's some more examples. Come on. You do a race. Oh, and there's the correct answer. So that was correct. Okay, I think I'll stop and save this part for Wednesday's video for Wednesday's activities. Okay? All right, have a great afternoon.